What if I told you our solar system has a hidden boundary, billions of kilometers away, where icy objects drift silently in the dark? Beyond Neptune and Pluto lies a largely unexplored frontier, a distant region filled with icy bodies and remnants from the solar system's birth. While the planets are well mapped, this outer edge remains mostly invisible, known only through the behavior of comets and hints from spacecraft. It's a mysterious threshold where the familiar solar system fades into the unknown. Beyond Neptune and Pluto, the solar system stretches into a vast and largely unexplored frontier, a region where our conventional maps of planets and moons no longer apply. This outer domain is a place of extremes, where sunlight is faint, temperatures plunge near absolute zero, and the influence of the sun's gravity is weak yet persistent enough to hold distant objects in elongated orbits. Astronomers call this region the trans-Neptunian space, encompassing the Kuiper belt, scattered disk, and eventually extending into the far reaches of the hypothesized Oort cloud. Unlike the inner solar system, where planets follow relatively predictable, nearly circular paths, the orbits here can be highly eccentric and tilted, hinting at a dynamic past shaped by gravitational nudges, collisions, and possibly even unseen massive objects lurking in the distance. The edge of the solar system is not a simple line, but a gradient where the influence of the sun gradually diminishes and interstellar space begins to dominate. This frontier is home to countless icy bodies, small rocky remnants, and comets, many of which preserve the primordial materials from the solar system's formation over 4.5 billion years ago. These objects are often faint, invisible to even our most powerful telescopes, making this region one of the last true frontiers of direct solar system exploration. Despite its remoteness, this edge has a profound impact on the inner solar system. The occasional journey of a long-period comet from these distant reaches into the inner planets reminds us that this boundary, though invisible and distant, is very much connected to our cosmic neighborhood. Even spacecraft that have traveled far beyond the planets, such as Voyager 1 and 2, have only begun to provide hints of this frontier, detecting the thinning influence of the solar wind and the interstellar medium. Yet, these missions have not come close to directly observing the vast populations of icy bodies lurking beyond Pluto, meaning most of this frontier remains theoretical, inferred from the movement of comets and subtle gravitational effects. The edge of the solar system, therefore, is a region of both extremes and possibilities, cold, dark, and largely inaccessible, yet holding the keys to understanding the origins, structure, and evolution of our solar system itself. The Kuiper belt and the Oort cloud are two of the most fascinating structures at the outer limits of our solar system, yet they are profoundly different in both location and shape. The Kuiper belt lies just beyond Neptune, starting at about 30 astronomical units, AU, from the Sun, and extending out to roughly 50 AU. This region is relatively close in cosmic terms and forms a flat, disc-shaped ring of icy bodies and dwarf planets, including well-known objects like Pluto, Haumea, and Makemake. These objects follow roughly circular, plane-aligned orbits around the Sun, much like the planets, which is why the Kuiper belt is sometimes described as the solar system's extended neighborhood. It contains thousands of small icy worlds, remnants from the early solar system that never coalesced into full-fledged planets, offering a window into the processes that shaped our planetary system. In contrast, the Oort cloud is vastly more distant, stretching anywhere from 2,000 AU to potentially 100,000 AU from the Sun, forming a nearly spherical shell surrounding the solar system. Unlike the flat Kuiper belt, the Oort cloud's objects occupy orbits in every conceivable direction, creating a three-dimensional cloud that envelopes the Sun and the planets like a giant icy cocoon. These objects are much smaller, colder, and far harder to detect, essentially invisible with current observational technology. While the Kuiper belt acts almost like a closer, denser belt of icy debris, the Oort cloud represents the extreme outermost boundary of the Sun's gravitational influence, a transitional zone to the interstellar medium. The distinction between these two regions is also evident in their dynamical behavior. Kuiper belt objects are influenced primarily by Neptune's gravity, which can nudge them into slightly eccentric orbits, occasionally sending them inward as short-period comets. Meanwhile, the Oort cloud is more tenuously bound to the Sun, and its objects are more easily perturbed by passing stars, molecular clouds, or galactic tidal forces. These perturbations can send a dormant comet on a million-year journey toward the inner solar system, creating the spectacular long-period comets that appear seemingly from nowhere. Studying both the Kuiper belt and Oort cloud not only helps us map the structure of our solar system, but also provides critical clues about its formation and the gravitational influences that have shaped it over billions of years. The Oort cloud exists at a staggering distance from the Sun, a scale that challenges our intuition and makes even the farthest planets seem close by comparison. Estimates place its inner edge at roughly 2,000 astronomical units, AU, from the Sun, an AU being the average distance between Earth and the Sun, about 150 million kilometers. To put this in perspective, Neptune orbits at just 30 AU, meaning the inner Oort cloud begins almost 70 times farther from the Sun than Neptune. Its outer edge could stretch as far as 100,000 AU, nearly halfway to the nearest star system, Alpha Centauri, which lies about 268,000 AU away. This enormous range creates a spherical region that completely dwarfs the rest of the solar system, making it a truly remote and almost inaccessible frontier. The scale of the Oort cloud explains why direct observation has remained impossible. Even the largest telescopes cannot resolve objects so faint and so distant, and no spacecraft has yet traveled anywhere near its inner boundary. The distances involved also mean that gravitational interactions are extremely weak. Objects in the outer Oort cloud barely feel the Sun's pull, so passing stars or the galactic tidal forces exert a significant influence, nudging comets into new orbits or occasionally sending them plunging into the inner solar system. This vast distance also means that any journey to the Oort cloud with current technology would take tens of thousands of years, making it a place more accessible to theoretical study than practical exploration, for now. Understanding this distance scale is crucial for appreciating the Oort cloud's role as a repository of primordial material, a slow-moving boundary to our solar system, and a source of the long-period comets that occasionally light up our night skies. Its sheer remoteness emphasizes how little we have explored beyond the planetary neighborhood, highlighting the limits of human observation and the immense challenges of reaching these icy sentinels at the edge of the Sun's gravitational domain. The story of the Oort cloud's discovery begins not with a telescope or spacecraft, but with careful observation and calculation. In the 1950s, Dutch astronomer Jan Oort noticed a peculiar pattern in the trajectories of long-period comets. Those rare comets that appear from the farthest reaches of space, with orbits lasting tens of thousands or even millions of years. These comets seem to originate from a spherical distribution surrounding the Sun rather than from the flat plane of the planets. Intrigued by this pattern, Oort proposed that there must exist a vast, distant reservoir of icy bodies, far beyond the orbits of Neptune and Pluto, which occasionally gets disturbed and sends comets plunging into the inner solar system. Oort's theory was groundbreaking because it suggested the solar system had an enormous, previously unimagined component, one that had remained hidden simply because it was too distant and faint to observe directly. He deduced that the Sun's gravity must still extend out to this cloud, holding these icy objects loosely in place, while external forces like passing stars and galactic tides could occasionally perturb them. The concept also provided an elegant solution to a long-standing puzzle: the origin of long-period comets. Before Oort, astronomers struggled to explain how these comets could appear suddenly in our skies without a detectable source. His hypothesis elegantly accounted for both their sudden appearances and their highly varied orbital inclinations, implying a nearly spherical reservoir surrounding the Sun. The Oort cloud theory was initially speculative, as no one had directly seen its contents. Yet, over time, observations of comet trajectories, combined with improved understanding of celestial mechanics, have consistently supported Oort's predictions. Today, the Oort cloud stands as a testament to the power of deductive astronomy, showing that careful analysis and theoretical reasoning can reveal entire regions of space that are otherwise invisible. Although Jan Oort himself never directly observed the cloud, his 1950s theory laid the foundation for modern research into the distant edges of our solar system, inspiring generations of astronomers to consider the vast, icy frontier that surrounds us. The Oort cloud is a repository of some of the most ancient and primordial materials in the solar system, a cosmic museum frozen in time. Unlike the planets and moons, which have undergone extensive geological and atmospheric evolution, the objects in the Oort cloud have remained largely untouched since the solar system's formation over 4.5 billion years ago. Its composition is dominated by icy bodies, including water ice, ammonia, methane, and carbon monoxide ices, mixed with rocky and metallic fragments. These are the building blocks that never coalesced into planets, representing remnants of the primordial solar nebula, the cloud of gas and dust from which the Sun and planets originally formed. Each of these objects is effectively a frozen time capsule, preserving chemical signatures and structures that can tell us about the early solar system, including the temperature gradients, the distribution of volatile compounds, and the processes that influenced planet formation. Comets are the most recognizable inhabitants of the Oort cloud, although they remain dormant for most of their lives. Far from the Sun, these icy bodies are inert, their volatile compounds frozen solid in the extreme cold of the outer reaches, sometimes just a few kilometers in diameter. Only when a comet is nudged from its distant orbit toward the inner solar system by a gravitational disturbance, whether from a passing star, a galactic tidal force, or the hypothetical influence of a distant planet, does it awaken. As it approaches the Sun, the heat causes the ices to sublimate, releasing gas and dust to form the characteristic glowing coma and trailing tails that we observe from Earth. While the Oort cloud contains countless comets of varying sizes, from small chunks less than a kilometer wide to massive bodies tens of kilometers across, the majority are likely small, icy fragments that have evaded detection due to their distance and faintness. In addition to these cometary nuclei, the Oort cloud likely contains icy rocks, objects that are composed of a mixture of rock and ice, sometimes with organic compounds embedded within. These are thought to be leftovers from the era of planetary formation, material that never accreted into larger bodies due to the weak gravitational environment at the edges of the solar system. They may include silicate-rich fragments or metallic cores of larger objects that disintegrated over time. Some theories suggest that interstellar objects, captured during the Sun's early formation in a dense stellar nursery, might also be present in the Oort cloud, representing an even older or more exotic class of material. This mix of icy and rocky material creates a heterogeneous environment where the diversity of composition can provide clues about the range of conditions in the early solar system. The Oort cloud's material is also significant for understanding the distribution of volatiles in the solar system. The ices stored in these distant objects are not merely passive remnants. They act as archives of the chemical inventory of the proto-solar nebula. By analyzing the chemical composition of comets that originate from the Oort cloud, scientists can infer the relative abundances of elements and compounds that existed during the formation of the Sun and planets. For example, the presence of complex organic molecules in comets suggests that the seeds for life's building blocks may have existed throughout the early solar system and possibly been delivered to the inner planets through cometary impacts. This has profound implications not only for planetary science, but also for astrobiology, as it hints at the universality of the ingredients for life. Despite its distance, the Oort cloud is not a static environment. While the individual objects move slowly in their distant orbits, gravitational interactions can occasionally alter their trajectories. Passing stars, molecular clouds, or the gravitational pull of the Milky Way's disk can perturb objects, sending them on paths toward the inner solar system or slightly adjusting their positions within the cloud. Collisions between objects are exceedingly rare due to the enormous distances between them, but they are not impossible and could create smaller fragments that contribute to the population of long-period comets. Over billions of years, these subtle dynamics have shaped the cloud structure and continue to influence the flux of comets reaching the inner planets. Moreover, the Oort cloud serves as a kind of natural laboratory for understanding the outer solar system's boundary conditions. The objects here are only weakly bound to the Sun, meaning that their orbits can be easily altered by even small external forces. This tenuous gravitational connection explains why the cloud extends so far, forming a nearly spherical shell around the Sun. Its composition, largely unaltered since the formation of the solar system, makes it a repository of primordial matter that is otherwise inaccessible elsewhere in the solar system. Unlike the Kuiper belt, where collisions and gravitational interactions with Neptune have significantly altered the population, the Oort cloud preserves a relatively untouched record of the early solar system's inventory of ices, rocks, and volatiles. The Oort cloud's composition is a blend of icy bodies, rocky fragments, and primordial material, serving as both a source of long-period comets and a fossil record of the early solar system. Its members are frozen, ancient, and distant, moving in slow orbits dictated by the Sun's fading gravitational pull and the subtle influences of galactic forces. By studying the occasional comet that journeys inward, scientists can peer into the chemical and physical conditions that existed billions of years ago, gaining insight into how our solar system formed and evolved. The Oort cloud is more than a boundary. It is a frozen archive, a cosmic library of materials and processes that shaped not only our planetary system, but potentially the broader story of life's chemical origins in the cosmos. The Oort cloud is unique among the structures of our solar system for its nearly perfect spherical shape, enveloping the Sun like a colossal icy shell. This configuration contrasts sharply with the flat, disc-like arrangements of the planets, the asteroid belt, and even the Kuiper belt. The spherical nature of the Oort cloud arises primarily from the mechanics of its formation and the gravitational influences acting upon it over billions of years. When the solar system was young, countless icy planetesimals were scattered outward by the gravitational forces of the giant planets, Jupiter, Saturn, Uranus, and Neptune. Some of these bodies were ejected completely into interstellar space, while others were captured into distant orbits that were largely free from the plane of the solar system. Over time, this scattering process, coupled with subtle perturbations from passing stars and the tidal forces of the Milky Way, randomized the inclinations of these distant objects' orbits, creating a roughly spherical distribution. Unlike the Kuiper belt, which remains in the plane of the planets due to the dominant influence of Neptune's gravity, The Oort cloud objects are so far from the Sun that its gravitational pull is weak, allowing external forces to exert a much larger effect over millions of years. The result is a nearly isotropic shell of icy bodies that surrounds the solar system in all directions. This spherical arrangement also explains why long-period comets, which originate from the Oort cloud, appear to come from random directions in the sky. Unlike short-period comets from the Kuiper belt, which follow orbits roughly aligned with the plane of the solar system, Oort cloud comets can descend toward the inner solar system from any angle, giving the appearance of an isotropic distribution. The spherical shape is further influenced by what astronomers call the Hills cloud, or inner Oort cloud, a denser, more tightly bound region closer to the Sun. While the outer Oort cloud extends tens of thousands of AU, the inner cloud provides a more stable reservoir of icy bodies that serve as a backup source for comets over cosmic timescales. Both regions contribute to the overall spherical geometry, but the outer Oort cloud dominates the apparent isotropy, with objects moving in highly elongated orbits that can extend to the limits of the Sun's gravitational influence. This vast shell effectively forms a protective envelope, encompassing not just the planets and Kuiper belt, but the entire heliosphere and the outer edge of solar influence. Interestingly, the spherical nature of the Oort cloud also highlights the interplay between the Sun and the galactic environment. Galactic tides, weak gravitational forces exerted by the Milky Way's mass distribution, slowly perturb the orbits of Oort cloud objects, further randomizing their trajectories and reinforcing the spherical distribution over billions of years. Occasionally, passing stars or molecular clouds exert stronger gravitational nudges, sending some of these icy bodies inward as long-period comets. These events illustrate how the spherical structure is not merely static, but a dynamic product of both solar and galactic influences, a living system in slow motion on cosmic timescales. Another fascinating implication of the spherical shape is its role as a boundary marker for the solar system. While the planets and Kuiper belt objects clearly define the inner structure, the Oort cloud forms a vast, three-dimensional envelope that marks the outermost reach of the Sun's gravitational dominion. This shell extends so far that it nearly blends into the surrounding interstellar medium, providing a soft but discernible transition between solar influence and the gravitational domain of the galaxy at large. In essence, the Oort cloud is both a physical and conceptual boundary, a frozen, spherical frontier that hints at the transition from the solar neighborhood to the broader cosmos. The spherical shape also preserves the long-term stability of these distant icy objects. By being isotropically distributed, collisions are exceedingly rare, and the gravitational interactions between objects are minimal, allowing them to remain largely unchanged over billions of years. This stability makes the Oort cloud a remarkable time capsule, holding material from the early solar system in pristine condition. Each object within this spherical shell is a remnant of the solar system's formative era, offering scientists a glimpse into the primordial conditions that existed when the Sun and planets were first taking shape. The Oort cloud's spherical geometry is a natural consequence of its formation and the gravitational forces acting over immense distances and timescales. It stands in stark contrast to the flat plane of the planets and the Kuiper belt, reflecting the weak solar gravity at these distances and the cumulative influence of galactic forces and passing stars. This spherical shell surrounds the Sun in all directions, providing both a source of long-period comets and a preserved record of the solar system's earliest materials. Its geometry emphasizes the vastness of the solar system, reminding us that the familiar plane of planets is just a small slice within a much larger, three-dimensional icy frontier. The Oort cloud is not a uniform structure. It is divided into two distinct regions: the inner Oort cloud, often referred to as the Hills cloud, and the outer Oort cloud. These two regions differ significantly in their distances from the Sun, density of objects, orbital stability, and roles in supplying comets to the inner solar system. The inner Oort cloud lies closer to the Sun, roughly spanning from about 2000 AU to 20,000 AU. This region is denser than the outer Oort cloud, meaning the objects are more tightly packed and gravitationally bound. Because of this, the inner Oort cloud serves as a long-term reservoir of icy bodies that are less susceptible to disruption from passing stars or galactic tides. While the objects here are largely inert, they are occasionally nudged into elongated orbits that can eventually send them toward the inner solar system, though this happens much less frequently than from the outer Oort cloud. The outer Oort cloud, by contrast, extends from approximately 20,000 AU out to as far as 100,000 AU, approaching the Sun's gravitational boundary with interstellar space. Here, the icy bodies are far more loosely bound to the Sun, and the space between them is enormous. This low-density environment means that even small perturbations, such as the passage of a nearby star, the gravitational influence of the Milky Way's galactic disk, or even molecular clouds in the galaxy, can significantly alter an object's orbit. These perturbations are what send long-period comets hurtling toward the inner solar system, giving humanity glimpses of these ancient frozen remnants. The outer Oort cloud, therefore, functions as the primary source of the long-period comets that appear with little warning and often from random directions, creating the isotropic distribution observed in cometary trajectories. The distinction between the inner and outer Oort cloud also reflects differences in orbital stability. Objects in the inner Oort cloud are more gravitationally stable, with their orbits largely preserved over billions of years. This stability makes the inner region a kind of insurance policy for the solar system, preserving material that could eventually replenish the outer cloud if objects are ejected or lost. The outer Oort cloud, on the other hand, is dynamic and vulnerable. Because objects are so loosely bound, even minor forces can cause them to leave the solar system entirely or to travel inward on long, eccentric orbits. This constant interplay between stability and instability ensures that the Oort cloud is both a long-term storage of primordial material and an active contributor to the inner solar system's comet population. Another key difference lies in the composition and potential origins of these two regions. While both contain icy bodies, rocks, and frozen volatiles, the inner Oort cloud may have more objects that originated closer to the Sun, scattered outward during the early chaotic period of planetary formation. The outer Oort cloud likely contains a mix of such scattered objects and bodies that were more gently nudged outward or even captured from the surrounding interstellar environment during the Sun's birth cluster. This makes the outer Oort cloud more diverse in terms of orbital inclinations and eccentricities, reflecting the cumulative gravitational influences over billions of years. The inner versus outer distinction also helps explain the timing and frequency of comet appearances. Short-lived perturbations in the outer Oort cloud can send comets inward relatively quickly on astronomical timescales, while the inner Oort cloud acts as a more gradual source, slowly feeding the outer region over eons. In effect, the inner Oort cloud maintains the long-term stability and replenishment of the cloud system, while the outer region provides the dynamic interface that interacts with the rest of the galaxy, sending comets on dramatic, observable journeys toward the inner solar system. This two-tiered structure creates a complex yet elegant system, a dense, stable core surrounded by a vast, loosely bound outer shell that both preserves and occasionally delivers ancient solar system material. Understanding the differences between the inner and outer Oort cloud is crucial for appreciating how our solar system maintains a reservoir of primordial material while simultaneously providing a source of long-period comets. The inner region acts as a secure vault, storing material for billions of years, whereas the outer region is the active frontier, responsive to external galactic forces and responsible for the occasional cometary visitor. This dynamic system highlights the interplay between stability and chaos at the edge of the Sun's influence, demonstrating that the solar system's outer boundary is not merely a passive collection of objects, but a complex and evolving structure shaped by both internal and external forces over the course of cosmic history. The Oort cloud is most famous for being the origin of long-period comets, those rare and spectacular celestial visitors whose orbits can span tens of thousands to millions of years. These comets appear suddenly in our skies, often without any predictable pattern, coming from directions seemingly at random. Their unexpected appearances puzzled astronomers for centuries because the flat, predictable plane of the planets and the Kuiper belt could not account for the isotropic distribution of these icy wanderers. It was Jan Oort's insight in the 1950s that solved this mystery. He proposed that a distant, spherical reservoir of icy bodies surrounded the Sun, and that occasional gravitational nudges could send these bodies plunging toward the inner solar system. The Oort cloud, therefore, acts as a cosmic launchpad for long-period comets, storing these icy remnants for billions of years until they are set on their dramatic journeys. The mechanism that sends these comets inward is rooted in the delicate balance of gravitational forces acting on objects at such extreme distances. The Sun's gravitational pull, though dominant closer in, is extremely weak in the Oort cloud, especially in the outer regions. This makes the comets highly susceptible to perturbations from external influences. Passing stars, which may drift relatively close to the solar system on astronomical scales, can slightly alter the orbits of these distant objects. Even small changes in velocity or trajectory caused by a nearby star or a dense molecular cloud can be sufficient to redirect a comet on a trajectory toward the inner solar system. Galactic tides, gradual gravitational forces from the mass of the Milky Way, also play a significant role, subtly reshaping the paths of Oort cloud objects over millions of years. In essence, the Oort cloud is a vast, fragile reservoir, primed to release comets when the smallest external disturbance occurs. Once nudged from their distant orbits, long-period comets embark on journeys that are not only long in distance, but also in time. Some may take millions of years to reach the inner solar system after being perturbed, traveling through the dark, cold expanse of the solar system almost unnoticed until they reach the Sun's warmth. During this journey, they retain the frozen ices and dust that make them unique, effectively carrying material that has remained unchanged since the early solar system. This explains why the chemical composition of long-period comets often differs from that of short-period comets from the Kuiper belt. They originate from regions far removed from planetary influences, preserving the primordial chemistry of the Sun's natal cloud. The unpredictability of long-period comet appearances is another direct consequence of their Oort cloud origin. Unlike comets from the Kuiper belt or scattered disk, which tend to follow relatively predictable orbits aligned with the solar system's plane, Oort cloud comets can arrive from any direction. Observers on Earth may notice a sudden new comet in the night sky without prior warning, often coming from an unexpected quadrant of space. This randomness reflects the spherical nature of the Oort cloud, where the comet's orbits are not confined to a single plane, but are distributed isotropically around the Sun. The sporadic arrival of these comets has fascinated humanity for millennia, often inspiring awe, fear, and speculation about cosmic cycles. The origin of these long-period comets also highlights the dynamic and interactive nature of the solar system's edge. The Oort cloud is not a static repository, but a region where gravitational forces from the Sun, nearby stars, and the galaxy continuously shape the trajectories of its objects. Over cosmic timescales, this interplay ensures a steady, though rare, supply of comets to the inner solar system, allowing us to observe material that has remained frozen for billions of years. Each new long-period comet is effectively a messenger from the distant reaches of our solar system, offering scientists a chance to study ancient ices, organic compounds, and primordial dust, and to gain insights into the conditions of the early solar system. Furthermore, the study of long-period comets has implications beyond just understanding the Oort cloud. By tracking their orbits and compositions, astronomers can infer the mass distribution, density, and structure of the Oort cloud itself, as well as the gravitational influences that operate at these extreme distances. The frequency, size, and chemical properties of these comets provide indirect evidence for the cloud's total population and the processes that govern its evolution. In many ways, long-period comets serve as probes, allowing humanity to explore a region that remains far beyond our current technological reach. They are emissaries from a frozen, distant wilderness, connecting the inner solar system with the vast, hidden frontier at its edge. The Oort cloud is the origin of long-period comets because it stores billions of icy remnants in a distant spherical reservoir, where weak solar gravity and external perturbations combine to send some of these objects on extraordinary, centuries or millennia-long journeys toward the Sun. Their sudden appearances in our skies are a direct manifestation of the Oort cloud's presence, a tangible reminder of the solar system's vast and largely unseen outskirts, and a window into the primordial materials from which our entire planetary system formed. The Oort cloud, despite being a distant and frigid realm, exists in a dynamic gravitational environment that constantly reshapes the orbits of its icy constituents. Unlike planets and Kuiper belt objects, whose paths are dominated primarily by the Sun's strong gravitational pull, the objects in the Oort cloud are only weakly bound to the solar system due to their extreme distance. This tenuous gravitational grip makes them highly sensitive to external forces, particularly the gravitational influences of passing stars and the broader gravitational field of the Milky Way galaxy, known as galactic tides. Together, these forces act as the primary agents responsible for nudging Oort cloud objects out of their distant, stable orbits and sending them on trajectories toward the inner solar system, transforming them into the long-period comets that occasionally grace our skies. Passing stars are perhaps the most dramatic and immediate gravitational influences. Over millions of years, stars in the Sun's galactic neighborhood move relative to our solar system, some coming close enough to exert a detectable gravitational effect on distant Oort cloud objects. A passing star does not need to be extremely close. Even a distance of a few light years can slightly perturb the orbit of a comet far out in the Oort cloud. This small nudge can increase the comet's orbital eccentricity, gradually elongating its path until it is directed inward toward the Sun. These interactions are generally rare, but given the vast timescales involved, billions of years, the cumulative effect of countless stellar passages has a profound influence on the Oort cloud's dynamics. In essence, every passing star is like a cosmic hand, subtly stirring the outer edges of the solar system and occasionally flicking a comet toward the inner regions. Galactic tides also play a crucial and more subtle role in shaping the orbits of Oort cloud objects. The Milky Way, with its enormous mass concentrated in a rotating disk, exerts a tidal gravitational force on objects within the galaxy, similar in concept to how the Moon generates ocean tides on Earth. While these galactic tides are minuscule when considered on short timescales or within the inner solar system, they accumulate significant effects over millions or billions of years in the distant reaches of the Oort cloud. This slow but persistent gravitational influence can slightly stretch or tilt the orbits of icy bodies, altering their inclination and eccentricity, and sometimes destabilizing them enough to send them spiraling toward the Sun. Importantly, galactic tides act in a nearly continuous manner, ensuring that Oort cloud objects are not completely static, but are subject to a slow evolution of their orbital parameters over time. The combination of these gravitational influences produces a natural mechanism for populating the inner solar system with long-period comets. Most Oort cloud objects remain dormant, moving in stable orbits for billions of years, but the occasional star passage or galactic tidal effect can dislodge an object from its distant perch. Once perturbed, a comet may travel hundreds to thousands of astronomical units inward, passing through regions where the Sun's gravity becomes increasingly dominant. During this inward journey, its orbit may be further modified by interactions with the giant planets or other comets, potentially leading to dramatic changes in speed and trajectory. The end result is the spectacular appearance of a long-period comet, often coming from an unexpected direction, as it ventures into the inner solar system for the first time in tens or hundreds of thousands of years. In addition to stars and galactic tides, other minor influences can also contribute to perturbations of Oort cloud objects. Large molecular clouds, for example, which are dense regions of gas and dust scattered throughout the Milky Way, can create localized gravitational fields strong enough to nudge distant icy bodies. Similarly, hypothetical massive objects in the outer solar system, sometimes proposed under the umbrella of Planet 9, could exert additional gravitational forces that affect the orbits of Oort cloud objects, subtly reshaping the distribution and frequency of cometary arrivals. Even the combined influence of countless small bodies in the outer solar system may collectively contribute to perturbations over geological timescales, though these effects are minor compared to stars and galactic tides. The timing and frequency of long-period comets reaching the inner solar system are direct consequences of these gravitational interactions. Studies of cometary orbits indicate that roughly one new long-period comet enters the inner solar system every year or two, though this is just a fraction of the total number of comets residing in the Oort cloud. The vast majority remain undisturbed, quietly orbiting the Sun at distances beyond the reach of any current spacecraft. Some estimates suggest that the Oort cloud may contain trillions of icy bodies, ranging from small kilometer-sized comets to larger tens-of-kilometer objects, meaning that even infrequent perturbations can result in a steady trickle of comets over cosmic timescales. This delicate balance between stability and external influence underscores the complex dynamical environment at the solar system's edge. Gravitational influences also help explain the isotropic distribution of long-period comets. Because the Oort cloud is roughly spherical, and perturbations from stars or galactic tides can occur from any direction relative to the Sun, comets are dislodged in essentially random trajectories. This isotropy contrasts with the relatively flat plane of the planets and Kuiper belt, where most short-period comets originate. The randomness of the comet's origins makes them appear unpredictable from Earth, often emerging in the sky without warning and from unexpected angles, a direct testament to the vast, three-dimensional gravitational theatre that governs the Oort cloud. Another critical aspect of these gravitational influences is their role in the long-term evolution of the Oort cloud itself. While some objects are nudged inward, others are sent outward, potentially escaping the Sun's gravity entirely and becoming interstellar objects traveling through the galaxy. This outward ejection helps maintain the overall structure and density of the cloud, preventing overcrowding and ensuring that the Oort cloud remains a vast, diffuse sphere over billions of years. The interplay between inward and outward trajectories maintains a dynamic equilibrium, balancing the influx of new comets with the loss of old or expelled objects. In this way, the gravitational influences of stars and galactic tides not only supply the inner solar system with long-period comets, but also preserve the long-term integrity of the Oort cloud as a distant reservoir of primordial material. Ultimately, the gravitational nudges from passing stars, galactic tides, and other subtle forces transform the Oort cloud from a static shell of icy bodies into a dynamic system, constantly evolving over cosmic timescales. Without these influences, the comets would remain forever frozen at the solar system's edge, invisible and inert. Instead, these forces orchestrate the slow, intermittent migration of material, sending frozen relics of the early solar system into the inner planetary region where they can be observed, studied, and admired. Every long-period comet that appears in our skies is a direct product of this gravitational ballet, a messenger from the distant, frozen periphery, carrying with it clues to the solar system's formation, composition, and ongoing interaction with the broader galaxy. The Oort cloud exists at the very edge of the Sun's gravitational influence, in a region where the pull of the solar system is extraordinarily weak and external forces play an outsized role in shaping the orbits of distant icy bodies. While passing stars and galactic tides are known to influence these objects, another, more mysterious factor may also be at play: dark matter. Dark matter is the elusive, invisible substance that is thought to make up approximately 85% of the matter in the universe. It does not emit, absorb, or reflect light, making it undetectable through traditional observational methods. Yet its gravitational influence is evident on the scale of galaxies, affecting the rotation curves of galaxies, the motion of galaxy clusters, and the bending of light around massive structures through gravitational lensing. Given its pervasive presence throughout the Milky Way, it is reasonable to speculate that dark matter might also exert subtle influences on objects in the Oort cloud, particularly at the extreme distances where the Sun's gravity weakens and external gravitational forces become more important. The idea that dark matter could influence Oort cloud objects arises from the fact that, unlike planets or Kuiper belt objects, these distant icy bodies are only tenuously bound to the Sun. The Oort cloud begins roughly 2,000 AU from the Sun and extends to 100,000 AU, distances at which gravitational perturbations from outside the solar system can nudge comets into the inner system. If dark matter is distributed in a diffuse halo around the Milky Way, as most models suggest, it would permeate the region of the Oort cloud. While its gravitational pull on any single object would be minuscule compared to that of a passing star or galactic tidal force, over millions or billions of years, even a slight influence could alter orbits, potentially changing the distribution of long-period comets or the dynamics of the cloud itself. In this sense, dark matter could act as a silent sculptor of the solar system's most distant boundary, subtly shaping the architecture of the Oort cloud over cosmic timescales. Some astrophysicists have proposed that localized variations in dark matter density, such as clumps or streams moving through the Milky Way, might produce measurable effects on the Oort cloud. These dark matter concentrations could generate additional gravitational perturbations, nudging comets inward or even ejecting them entirely from the solar system. While these effects would be extraordinarily small on human timescales, they could cumulatively contribute to the sporadic influx of long-period comets, complementing the influences of stars and galactic tides. In particular, dark matter's presence might help explain subtle anomalies in cometary distributions orbital inclinations, or frequencies that cannot be fully accounted for by visible matter alone. Essentially, dark matter could act as a hidden background force, quietly influencing the motions of distant solar system objects in ways we are only beginning to theorize. Furthermore, the Oort cloud's extreme distance makes it one of the few regions in the solar system where the influence of dark matter could be comparatively detectable, albeit indirectly. Within the inner solar system, the gravitational pull of the planets and the Sun dominates completely, effectively masking any effect dark matter might have. But at 50,000 to 100,000 AU, the Sun's grip is weaker, and the combined gravitational effects of stars, galactic tides, and potentially dark matter become comparable. In theory, careful study of the trajectories of newly incoming long-period comets might reveal subtle perturbations that hint at an unseen gravitational influence, providing an indirect method to probe the local dark matter environment. This is speculative, of course, and presents extraordinary observational challenges, but it highlights the Oort cloud's potential as a natural laboratory for studying not only the solar system, but also the elusive cosmic web of dark matter that permeates the galaxy. The interplay between dark matter and the Oort cloud also raises broader questions about the solar system's boundary and our understanding of gravitational forces in low-density regions. If dark matter contributes even minimally to the dynamics of distant objects, it might help explain the stability of the Oort cloud over billions of years. Without some stabilizing background influence, weakly bound objects could be more easily ejected by random stellar encounters or galactic tidal forces. In this scenario, dark matter might act as a subtle, omnipresent gravitational glue, maintaining the overall cohesion of the cloud and shaping the reservoir of icy bodies from which long-period comets emerge. While this remains highly theoretical, it underscores the complex interplay between visible and invisible matter in defining the outer reaches of the solar system. The mystery of dark matter's influence on the Oort cloud also invites speculation about its potential to interact with hypothetical objects in this region, such as the proposed Planet 9 or other massive yet undetected bodies. If a distant large object exists in the far reaches of the solar system, dark matter's gravitational influence could subtly alter its orbit over eons, in turn affecting the trajectories of nearby Oort cloud objects. This would add an additional layer of complexity to the already intricate gravitational interactions that govern this distant frontier. In essence, the Oort cloud may be subject to a multi-layered system of forces: the Sun's diminishing gravity, stellar flybys, galactic tides, hypothetical massive planets, and even the unseen influence of dark matter, all combining to orchestrate the slow, stochastic movements of its icy inhabitants. While the direct detection of dark matter remains one of the great challenges of modern physics, the Oort cloud presents a tantalizing cosmic laboratory where its influence might be inferred indirectly. The trajectories, arrival rates, and distribution of long-period comets, when analyzed over long timescales, could reveal patterns consistent with a weak, omnipresent gravitational field that is otherwise invisible. Such studies would require decades of observation and the development of precise models of cometary dynamics, taking into account all known forces. If dark matter does play a role, it would demonstrate that the Oort cloud is not merely the outermost icy shell of the solar system, but also a region where the interplay between visible and invisible matter becomes evident, connecting our local solar neighborhood to the broader structure of the galaxy. Ultimately, the speculation about dark matter and the Oort cloud highlights the profound uncertainty and mystery that surrounds the solar system's edge. It reminds us that even in a system we have studied for centuries, there are forces and influences beyond our immediate perception, shaping the motion of objects in ways that challenge conventional understanding. Dark matter may remain invisible and enigmatic, but its potential role in subtly influencing the Oort cloud adds yet another layer of complexity to the already fascinating dynamics of the solar system's most distant frontier. This interplay between the known and the unknown, the visible and the invisible, underscores why the Oort cloud continues to captivate scientists and space enthusiasts alike, offering a frozen laboratory for studying not only the early solar system, but also the fundamental forces that govern our galaxy. Observing the Oort cloud is one of the most formidable challenges in modern astronomy, and in fact, no object in the cloud has ever been directly imaged or observed. The reasons for this difficulty are rooted in the sheer vastness of the solar system's outer reaches and the physical characteristics of the objects themselves. The Oort cloud begins at roughly 2,000 astronomical units, AU, from the Sun, well beyond the orbit of Pluto and even the distant scattered disk objects in the Kuiper belt, and extends out to an estimated 100,000 AU, almost halfway to the nearest stars. At these distances, the sunlight reaching Oort cloud objects is minuscule, thousands of times weaker than the light falling on Earth, which means that even relatively large objects reflect extremely little light. A comet or icy rock tens of kilometers across would appear extraordinarily faint, essentially invisible to current telescopes, which are optimized for observing objects that are closer and brighter. Compounding the challenge is the fact that Oort cloud objects are typically small and dark. Most are cometary nuclei composed of ice mixed with dust and organic compounds, which have very low albedos, reflecting only a tiny fraction of incident sunlight. Their diminutive size, combined with the weak illumination, makes detection extraordinarily difficult. Even the most powerful ground-based and space telescopes, such as the Hubble Space Telescope or the upcoming James Webb Space Telescope, struggle to detect such faint, distant objects. Unlike planets, which may emit infrared radiation or can be observed due to reflected sunlight from their sizable surfaces, Oort cloud bodies are effectively invisible unless they are dislodged from their distant orbits and enter the inner solar system, where solar heating triggers sublimation and the formation of a bright coma and tail. Distance is another critical factor that hampers observation. At 2000 AU, an Oort cloud object is roughly 50 times farther from the Sun than Pluto, and the outermost objects are 50 times farther still. Light travels extremely slowly across such immense distances in terms of the tiny angular resolution we can observe from Earth, meaning that Oort cloud objects are effectively point sources of faint light that cannot be distinguished from the background noise of distant stars and galaxies. The faintness is exacerbated by the fact that these objects move slowly across the sky, so traditional motion-based detection methods, which work well for nearer asteroids or Kuiper belt objects, are less effective. In essence, the Oort cloud exists in a region where observational signals are exceedingly weak, and the cloud is so diffuse that the density of objects in any given patch of sky is incredibly low, providing almost no contrast against the cosmic backdrop. Technological limitations also play a role in why the Oort cloud remains unseen. While we have advanced detectors and imaging systems capable of capturing faint light, surveying the entire spherical volume of the Oort cloud is practically impossible with current instruments. Unlike the Kuiper belt, which lies roughly in the same plane as the planets and occupies a relatively narrow band of the sky, the Oort cloud is spherical, meaning it spreads across the entire celestial sphere. To detect objects in all directions would require a telescope capable of continuously monitoring vast swaths of the sky at extreme sensitivity, a feat not currently achievable. Even hypothetical surveys would need to differentiate between faint Oort cloud objects and countless background stars, galaxies, and interstellar debris, which presents a staggering computational and observational challenge. Another obstacle comes from the lack of natural illumination and the extreme cold of the Oort cloud. Solar radiation at these distances is too weak to significantly heat or illuminate objects, and the Oort cloud is far too cold to emit detectable infrared radiation on its own. The thermal signature of a small icy object so far from the Sun is essentially undetectable with present-day instruments. This contrasts with objects in the inner solar system or even the Kuiper belt, which, though cold, can emit some infrared radiation that allows for detection via space-based infrared telescopes. In the Oort cloud, the faintness and thermal invisibility render direct imaging virtually impossible. Because of these challenges, the existence of the Oort cloud is inferred primarily through indirect evidence, most notably the orbits of long-period comets. By analyzing the distribution, inclination, and trajectories of these comets, astronomers deduce the presence of a vast, spherical reservoir of icy bodies surrounding the Sun. This method of inference has been extraordinarily effective in understanding the cloud's structure, composition, and size, even in the absence of direct observation. Studies of cometary arrival rates and orbital characteristics also provide clues about the cloud's density, inner versus outer regions, and the dynamic processes that perturb objects into the inner solar system. The difficulty of observation is further compounded by the timescales involved. Objects in the Oort cloud move incredibly slowly along their orbits, taking millions of years to complete a single revolution around the Sun. This slow motion means that, from our perspective, they are nearly stationary in the sky over human timescales, making motion-based detection techniques ineffective. The combination of extreme distance, small size, low reflectivity, cold temperatures, and slow motion has thus kept the Oort cloud beyond the reach of direct observation, making it one of the most enigmatic and least understood regions of our solar system. This observational challenge underscores the need for indirect methods, including the study of long-period comets, simulations of the solar system's formation, and modeling of gravitational interactions with passing stars and galactic tides. It also fuels speculation about future technologies, such as powerful next-generation telescopes or even spacecraft capable of traversing the outer solar system, which could potentially detect or study these distant objects directly. Until such advancements are realized, the Oort cloud remains a theoretical yet highly compelling boundary to our solar system, a realm inferred from cosmic breadcrumbs rather than illuminated by human observation. It is a frozen, invisible frontier, holding the secrets of the solar system's formation and preserving material untouched for billions of years, waiting silently in the darkness for future exploration. The idea of a hypothetical Planet 9 has captivated astronomers and planetary scientists in recent years, and its potential influence on the Oort cloud adds another layer of intrigue to the solar system's distant frontier. Planet 9 is theorized to be a massive, unseen planet, several times the mass of Earth, orbiting the Sun far beyond the Kuiper belt, possibly hundreds of astronomical units away. Its existence has not been directly confirmed, but indirect evidence comes from the peculiar clustering of certain trans-Neptunian objects and extreme Kuiper belt orbits that suggest the gravitational influence of a massive, distant body. If Planet 9 does exist, it could have profound effects on the dynamics of the Oort cloud, shaping the orbits of icy bodies and potentially altering the frequency and trajectory of comets that enter the inner solar system. One of the primary ways Planet 9 could influence the Oort cloud is through gravitational perturbation. Even at a vast distance, the mass of such a planet would be sufficient to exert measurable gravitational forces on nearby Oort cloud objects, especially those in the inner Oort cloud, or Hills cloud, which lies closer to the Sun. These perturbations could subtly modify orbital inclinations and eccentricities, nudging some objects onto more elongated paths. Over millions of years, repeated interactions with Planet 9 could redirect a small fraction of Oort cloud comets toward the inner solar system, contributing to the long-period comet population in addition to the effects of passing stars and galactic tides. In this way, Planet 9 could serve as an unseen architect, shaping the distribution of distant icy bodies and influencing the observable cometary flux from the outer solar system. Planet 9's gravitational influence could also explain certain asymmetries in the Oort cloud structure. Observationally, the distribution of extreme Kuiper belt objects appears lopsided or clustered in a way that would be highly improbable without the presence of a massive perturber. If these patterns extend outward into the Oort cloud, they might indicate that Planet 9 not only affects the inner regions beyond Neptune, but also has a subtle yet long-reaching impact on the orbits of objects thousands of AU from the Sun. This could manifest as slight anisotropies in the otherwise nearly isotropic cloud, producing preferred directions from which comets are occasionally perturbed inward. Such asymmetries could help astronomers refine models of both Planet 9's orbit and the global structure of the Oort cloud, bridging the gap between theoretical predictions and observed phenomena. Additionally, Planet 9 could play a role in stabilizing or maintaining certain parts of the inner Oort cloud. While the outer Oort cloud is highly susceptible to external influences like passing stars and galactic tides, the inner region is more densely packed and gravitationally bound. A massive object like Planet 9 could serve as a long-term shepherd, exerting a gravitational influence that slightly confines or organizes some of these distant icy bodies. Over billions of years, this effect could help preserve the population of the inner Oort cloud, ensuring a steady reservoir of comets capable of replenishing the outer regions when other processes, such as stellar perturbations, remove or eject objects. In essence, Planet 9 could act as a subtle stabilizer within the solar system's distant frontier, influencing both the dynamics and the longevity of the Oort cloud. Planet 9's potential influence also extends to the generation of extreme cometary orbits. In certain scenarios, objects perturbed by Planet 9 could be sent into highly eccentric, inclined, or even retrograde orbits, eventually crossing paths with the inner solar system at unusual angles. This could help explain some long-period comets that do not conform to expected orbital distributions based solely on galactic tides or stellar encounters. By acting as an additional perturbative force, Planet 9 could increase the diversity of trajectories observed among comets, offering a plausible mechanism for the rare and unexpected cometary appearances that have puzzled astronomers for centuries. Its role in shaping these extreme orbits further underscores the interconnectedness of gravitational influences at the edge of the solar system. Speculation about Planet 9 also raises fascinating questions about the outer solar system's formation and evolution. If such a planet exists, it may have been scattered outward during the early chaotic period of planetary formation, perhaps during interactions with Jupiter, Saturn, Uranus, or Neptune. This scattering could have placed Planet 9 on a distant, elongated orbit, where it now resides as a hidden guardian of the solar system's outskirts. Its gravitational influence over billions of years would have quietly sculpted the Oort cloud, contributing to its spherical distribution, maintaining its stability, and occasionally nudging comets inward. In this way, Planet 9 would be a hidden participant in the solar system's long-term evolution, linking the distant cloud of icy bodies to the larger planetary architecture and to processes that occurred billions of years ago. The presence of Planet 9 could also have implications for the interaction between the Oort cloud and external galactic forces. While galactic tides and passing stars exert their influence on Oort cloud objects from outside the solar system, a massive planet within the system could amplify, redirect, or dampen some of these effects, acting as an intermediary gravitational force. For example, objects perturbed by galactic tides might first encounter Planet 9, which could further alter their trajectory, either stabilizing them in a new orbit or accelerating their journey toward the inner solar system. This complex interplay highlights the potential for Planet 9 to mediate the dynamics of the solar system's outermost region in ways that are still largely theoretical but deeply intriguing. Planet 9's potential impact underscores the broader significance of the Oort cloud as a dynamically responsive system. The cloud is not a static shell of icy debris, but a vast, interconnected region where internal and external gravitational influences combine to orchestrate the motion of billions of objects. A single massive yet undetected planet could have consequences that extend across tens of thousands of AU, affecting both the inner and outer Oort cloud, modulating the frequency of long-period comets and shaping the overall structure of the cloud. This adds an additional layer of mystery and complexity to the Oort cloud, demonstrating that the solar system's edge is not merely a passive boundary, but a dynamic, evolving frontier shaped by forces both known and speculative. Comets originating from the Oort cloud are among the most fascinating travelers in the solar system, embarking on journeys that span tens of thousands, and sometimes even hundreds of thousands, of astronomical units. Once gravitationally nudged from their distant, near-static orbits by passing stars, galactic tides, or possibly Planet 9, these icy bodies begin an epic voyage inward toward the Sun. The paths they follow are typically highly elongated, elliptical, or even near parabolic, taking them from the frigid, dark outskirts of the solar system, where temperatures approach absolute zero, to the relatively warm inner regions, where the Sun's radiation begins to profoundly alter their physical structure. The enormity of these distances is almost incomprehensible. A comet might spend millions of years traveling from the outer Oort cloud, covering distances so vast that its motion is almost imperceptible in human timescales, only to reach the inner solar system at high velocity, appearing suddenly as a luminous object streaking across the sky. The orbital dynamics of Oort cloud comets are largely dictated by the gravitational influence of the Sun once they are dislodged from their distant positions. Their nearly parabolic orbits mean that the Sun's gravity dominates their path during the inward journey, pulling them ever faster as they approach perihelion, the closest point to the Sun. These trajectories often bring comets from virtually any direction in the sky, a consequence of the isotropic distribution of the Oort cloud itself. Unlike Kuiper belt comets, which follow orbits largely confined to the plane of the solar system, Oort cloud comets can arrive from steep inclinations, high latitudes, or even retrograde paths, making their appearances unpredictable. This randomness in direction and trajectory has been one of the key clues to the existence of a distant, spherical reservoir of icy bodies surrounding the Sun. As these comets approach the inner solar system, the increasing intensity of solar radiation begins to trigger dramatic physical changes. The extreme cold of the Oort cloud means that comets are initially frozen solid, composed of water ice. Frozen gases such as carbon monoxide, carbon dioxide, methane, ammonia, and dust particles intermixed with organic compounds. As they near the Sun, the rising temperatures cause sublimation, the process by which solid ices transform directly into gas. This gas escapes from the comet's nucleus, carrying with it dust and small particles, forming a glowing atmosphere known as a coma. The coma can expand thousands of kilometers in diameter, making the previously invisible comet suddenly observable. The solar wind and radiation pressure then shape the escaping gas and dust into tails. Typically, one tail composed of ionized gas that points directly away from the Sun, and a second tail of dust particles that curves along the comet's orbit. These tails, luminous and often spectacular, are the visual signatures by which we recognize long-period comets from Earth. The behavior of Oort cloud comets is also shaped by the sheer scale of their orbits. Because these bodies originate so far from the Sun, their inbound speeds increase dramatically as they fall into the inner solar system, sometimes reaching tens of kilometers per second. At perihelion, this kinetic energy is at its maximum, and sublimation rates peak, creating highly active comas and tails. However, once the comet passes the Sun and moves outward again toward aphelion, the decreasing solar radiation allows the gas to freeze once more, returning the comet to a dormant, almost inert state. This cyclical transformation means that Oort cloud comets can remain largely unaltered for billions of years until the rare event occurs in which they are nudged inward. Each visit to the inner solar system is both a fleeting spectacle and a window into the primordial materials that formed the solar system. Interestingly, the extreme distance of their origin means that Oort cloud comets often travel nearly the entire breadth of the solar system over their lifetimes. From hundreds or thousands of AU away, the journey inward involves traversing regions dominated by the gravitational influences of the giant planets, Jupiter, Saturn, Uranus, and Neptune, which can further modify their orbits. A close encounter with a giant planet can either deflect a comet onto a new path, potentially ejecting it entirely from the solar system, or capture it into a shorter period orbit, transitioning it from a long-period Oort cloud comet to a more familiar Jupiter family or Halley-type comet. This gravitational interplay adds another layer of complexity, creating a wide variety of possible orbital outcomes and highlighting the dynamic nature of cometary trajectories in the solar system. The unpredictability of comet behavior also stems from non-gravitational forces, particularly outgassing. As volatile ices sublimate unevenly from the comet's nucleus, they produce jets that can subtly alter the comet's trajectory. These forces, though small compared to solar gravity, are significant when multiplied over millions of kilometers, slightly bending or shifting the comet's path. This can result in observable deviations from predicted orbits, making long-term trajectory forecasting a challenging task. Each comet therefore represents a complex interplay of gravitational and non-gravitational forces, shaped by its origin in the remote Oort cloud and its passage through the dynamic solar system environment. The behavior of these comets also has profound implications for the Earth and the inner solar system. Long-period comets can deliver water, organic molecules, and other primordial material to the inner planets, including Earth, potentially influencing the development of life. The composition of comets reflects the pristine, unaltered matter from the early solar system, acting as time capsules that preserve clues about the conditions under which planets formed. Studying the coma, tails, and chemical makeup of Oort cloud comets provides invaluable insight into the primordial materials that existed more than 4 billion years ago, offering a glimpse into the early processes of planetary formation, chemical evolution, and the solar system's infancy. The enormous scale of Oort cloud comet journeys, combined with their dramatic transformation near the Sun, reinforces the notion of the solar system as a vast and interconnected system. These comets serve as messengers from the distant, frozen periphery, linking the farthest reaches of the Sun's influence with the inner planetary environment. Their behavior and orbits illustrate the dynamic nature of the solar system's edge, a place where distance, gravity, and the Sun's energy interact to create phenomena that are both scientifically significant and visually spectacular. Each comet that appears in our sky is a testament to the Oort cloud's existence, a bridge between the invisible frontier at the edge of our solar system and our immediate observational world, revealing the ongoing dialogue between the Sun, its distant companions, and the broader galaxy. The Oort cloud can be considered one of the most remarkable time capsules in the solar system, a frozen archive preserving the primordial materials from the era of planetary formation over 4 billion years ago. Unlike the planets, moons, and even asteroids that have been altered by collisions, volcanic activity, atmospheric processes, or solar radiation over billions of years, the icy bodies of the Oort cloud have largely remained untouched since their formation. Their isolation in the extreme cold and darkness of the solar system's outermost regions has shielded them from the intense heat and solar wind that modify materials closer to the Sun, allowing them to retain their original composition, structure, and chemical signature. In this sense, the Oort cloud is not just a distant boundary of our solar system, but a deep repository of ancient matter, a relic of the protoplanetary disk from which the planets, moons, and other smaller bodies originated. The composition of Oort cloud objects reveals why they are such compelling time capsules. These icy bodies are a mixture of water ice, carbon dioxide, methane, ammonia, and complex organic compounds embedded with dust and silicate grains. These materials are the building blocks of the solar system, formed from the primordial gas and dust that surrounded the Sun during its earliest stages. By studying comets that originate from the Oort cloud, astronomers gain a unique glimpse into the chemical environment of the early solar system. Unlike meteorites, which may have experienced heating and differentiation, or asteroids, which may have undergone collisions and partial melting, Oort cloud comets preserve the conditions of the protoplanetary disk almost exactly as they were billions of years ago. They are essentially pristine samples left frozen and unaltered in the dark recesses of the Sun's gravitational domain. These icy bodies are particularly important for understanding the distribution of volatile materials in the early solar system. Volatiles, substances that easily vaporize at relatively low temperatures, play a crucial role in planetary formation, the development of atmospheres, and even the emergence of life. The Oort cloud, by harboring a vast reservoir of such materials far from the Sun, provides insight into how these substances were distributed in the outer regions of the protoplanetary disk. The chemical ratios preserved in Oort cloud comets, including isotopic signatures of hydrogen, carbon, nitrogen, and oxygen, offer clues about the temperature gradients and chemical reactions that took place during the solar system's formation. Each comet that journeys inward becomes a messenger, carrying information about these conditions directly to Earth, where spectroscopic studies can decode its chemical composition. Moreover, the Oort cloud serves as a record of dynamical processes from the solar system's formative years. Many of the comets and icy bodies in the Oort cloud were likely ejected from the region of the giant planets, Jupiter, Saturn, Uranus, and Neptune, during the chaotic period of early planetary migration. Gravitational interactions between these massive planets and smaller planetesimals scattered countless icy bodies outward, depositing them in the distant reaches of the solar system. In this sense, the Oort cloud is not just a static repository of ancient matter. It is also a record of the solar system's violent and dynamic early history. The spatial distribution, orbital parameters, and density of these bodies encode information about the timing, magnitude, and sequence of events that shaped the current architecture of the solar system, effectively serving as a historical record written in ice and rock. The preservation of these ancient materials has implications that extend beyond our solar system as well. Some theories suggest that comets from the Oort cloud could have delivered water and organic molecules to the inner planets, including Earth, during the heavy bombardment period early in our planet's history. If true, these comets may have contributed to the initial inventory of materials essential for life, making the Oort cloud not just a passive archive, but an active contributor to planetary habitability. The organic compounds found in cometary comas, including amino acids and complex hydrocarbons, mirror the fundamental building blocks of life, highlighting the potential significance of these distant objects in the broader cosmic narrative of biology and chemistry. Studying the Oort cloud also allows scientists to trace back the solar system's evolution and compare it to other planetary systems in our galaxy. By examining the properties of long-period comets and their trajectories, astronomers can infer the mass distribution, stability, and evolutionary history of the cloud, gaining insights into the processes that might operate in other stellar systems with distant cometary reservoirs. The Oort cloud thus serves as both a local archive of our solar system's infancy and a template for understanding how planetary systems throughout the Milky Way might form and evolve over billions of years. The Oort cloud's role as a cosmic time capsule is further emphasized by its ability to preserve isotopic and chemical ratios that remain largely unchanged over billions of years. Unlike objects closer to the Sun, which may undergo differentiation, heating, or chemical alteration due to solar radiation, Oort cloud bodies maintain their primordial states. Spectroscopic analysis of comets provides direct access to this frozen record, revealing the chemical fingerprints of the early solar nebula. Each comet becomes a probe into an epoch long before the Earth itself existed, carrying unaltered information about the environment in which the Sun and its planets formed. These studies not only enhance our understanding of the solar system's birth, but also inform models of planetary formation in general, providing a comparative framework for exoplanetary systems. In addition to chemical preservation, the Oort cloud protects its inhabitants from collisional erosion and disruptive processes. In the dense inner regions of the solar system, collisions between asteroids and other debris are common, leading to fragmentation, melting, and surface alteration. By contrast, the extreme isolation of the Oort cloud ensures that most objects remain intact, effectively preserving their primordial structure. The low density of the cloud minimizes interactions between its constituents, allowing the original accretionary properties, porosity, and surface compositions of these bodies to remain virtually untouched. This makes them ideal for studying the early conditions of planetesimal formation, aggregation, and the initial stages of solar system chemistry. The Oort cloud's status as a time capsule underscores the urgency and value of future exploration. While the indirect study of comets provides substantial insights, direct observations or missions to the cloud could revolutionize our understanding of the solar system's early materials. Retrieving samples or even conducting close-range observations of Oort cloud objects could provide unprecedented chemical, isotopic, and structural information, revealing details that are impossible to obtain from Earth-based observations alone. Such missions would allow humanity to access the primordial building blocks of the solar system, frozen in a region untouched by billions of years of solar and planetary activity, offering an unparalleled glimpse into the universe's formative processes. The Oort cloud is more than a distant boundary. It is a cosmic archive, preserving the earliest materials, the dynamical history, and potentially even the seeds of life that originated in the solar system. Each comet that journeys inward from this frozen frontier carries with it a fragment of our system's infancy, a messenger from a time before the planets coalesced, before Earth even existed, and before the Sun reached its current stability. In this way, the Oort cloud acts as both a repository of ancient knowledge and a bridge across time, connecting us to the origins of our solar system, offering a tangible link to a distant, frozen past that continues to shape our understanding of the cosmos. The Oort cloud exists at the extreme boundary of the Sun's gravitational influence, and it sits in close conceptual and physical relation to the Heliosphere, which defines the outermost limits of the Sun's energetic and magnetic dominance. The heliosphere is essentially a bubble carved out of the interstellar medium by the solar wind, a continuous outflow of charged particles emitted by the Sun. This bubble extends far beyond the orbits of the outer planets, providing a protective cocoon that shields the inner solar system from a significant portion of cosmic radiation and interstellar particles. The Oort cloud, lying just beyond the effective reach of the planets and the Kuiper belt, intersects with this region of transition between the Sun's influence and the interstellar medium, positioning it at the very edge of the solar system as we understand it. The heliosphere itself has multiple boundaries, each marking different physical transitions in the solar wind and the influence of interstellar forces. The first major boundary is the termination shock, where the solar wind slows from supersonic to subsonic speeds due to interactions with the surrounding interstellar medium. Beyond this lies the heliosheath, a turbulent region in which the slowed solar wind continues to push against interstellar particles. The outermost boundary is the heliopause, the point at which the pressure of the solar wind balances with the pressure of the surrounding interstellar medium. It is effectively the edge of the Sun's sphere of influence in terms of particle outflow and magnetic field dominance. The Oort cloud begins beyond the gravitationally dominated regions of the planets, but remains within the Sun's gravitational sphere of influence, overlapping conceptually with the outer heliospheric boundaries. While the heliopause marks a limit to the Sun's solar wind, the Oort cloud marks a boundary in gravitational influence, extending the Sun's reach much farther into space than the heliosphere itself does in energetic terms. This positioning places the Oort cloud in a region of dynamic interaction between the solar system and interstellar space. Although the Sun's gravity still governs the orbits of Oort cloud objects, the extremely weak gravitational binding at these distances makes them highly susceptible to external perturbations. Passing stars, molecular clouds, and the galactic tidal forces generated by the Milky Way's mass distribution can easily nudge objects in the Oort cloud, occasionally sending comets spiraling toward the inner solar system. Additionally, the interstellar medium exerts a small but persistent influence through drag and collisions with gas and dust particles, subtly affecting the cloud's structure over astronomical timescales. In this sense, the Oort cloud exists in a transitional zone, a liminal space bridging the familiar solar-dominated region with the vast, largely unknown interstellar expanse. The connection between the Oort cloud and the heliosphere also highlights the protective and isolating functions of the Sun's extended influence. Inside the heliosphere, cosmic rays and interstellar particles are partially deflected by the Sun's magnetic field and solar wind. Once beyond the heliopause, as is the case in the Oort cloud's outer regions, objects are more exposed to interstellar radiation and cosmic particles. While the Oort cloud's distance provides natural insulation from solar heat and light, it does not shield these bodies from energetic particles streaming through interstellar space. This exposure over billions of years has allowed the Oort cloud to accumulate a subtle record of interstellar interactions, in addition to preserving primordial solar system material. In a sense, each Oort cloud object acts as a frozen witness to both the conditions of the early solar system and the ongoing influence of the galactic environment, residing at the intersection of solar and interstellar domains. Voyager 1 and Voyager 2 have provided our first direct glimpses of this boundary region. Both spacecraft crossed the termination shock and eventually the heliopause, moving into interstellar space while still within the Sun's gravitational influence. These observations illustrate how the solar wind's protective bubble eventually gives way to the interstellar medium, emphasizing the conceptual parallel between the heliosphere's limits and the outer reaches of the Oort cloud. While the Voyager spacecraft have not approached the Oort cloud itself, they remain within several hundred AU of the Sun, their measurements underscore the stark transition between solar and interstellar influences, the same environment in which Oort cloud objects reside on an ongoing basis. Furthermore, understanding the Oort cloud in relation to the heliosphere provides insight into the broader context of planetary systems and their interactions with the galaxy. The Sun's heliosphere is not a static structure. It moves through the Milky Way, encountering regions of varying interstellar density, magnetic fields, and radiation. The Oort cloud, as the Sun's distant reservoir of icy bodies, experiences these environmental changes indirectly through gravitational perturbations and exposure to cosmic particles. This ongoing interaction may influence the long-term stability of the cloud, its population of comets, and the likelihood of sending objects toward the inner solar system. In other words, the Oort cloud serves as a natural laboratory for studying the interface between a star's gravitational domain, its heliosphere, and the galactic environment at large. The connection to the heliosphere emphasizes the scale and grandeur of the solar system itself. While the planets, moons, and Kuiper belt objects occupy regions that are vast on a human scale, the Oort cloud and the heliospheric boundaries expand our conception of the solar system into a nearly unimaginable domain. The Oort cloud's icy bodies, resting at the fringe of gravitational influence, represent the ultimate threshold of the Sun's reach, extending our understanding of the solar system from the warmth of the inner planets to the cold, dark edge of interstellar space. This boundary is not merely a line on a map of space, but a dynamic, evolving region where the Sun's influence wanes, galactic forces dominate, and the interplay of gravitational, radiative, and magnetic forces shapes the distant frontier of our cosmic neighborhood. Humanity's exploration of the solar system has reached remarkable distances, but even the farthest traveling spacecraft have only begun to approach the outskirts where the Oort cloud resides. Voyager 1 and Voyager 2, launched in 1977, were designed to study the outer planets, but they ultimately became humanity's first emissaries to interstellar space. These spacecraft have provided invaluable insights into the heliosphere, the solar wind, and the cosmic environment at the edge of the Sun's influence. Voyager 1 crossed the heliopause in 2012 at a distance of about 121 astronomical units, AU, from the Sun, entering a region dominated by interstellar plasma and magnetic fields. Voyager 2 followed in 2018, crossing the heliopause at approximately 119 AU. These achievements offer the closest glimpse yet of the solar system's distant boundary, giving us direct measurements of the transition from solar to interstellar influence, but they remain thousands of times closer than the estimated inner boundary of the Oort cloud, which begins at roughly 2000 AU. Although Voyager has provided detailed data on the structure of the heliosphere, its observations only hint at the dynamics that govern the Oort cloud. The instruments aboard these spacecraft measure charged particles, magnetic fields, cosmic rays, and plasma waves, revealing how the solar wind diminishes and eventually yields to interstellar pressures. This information indirectly informs our understanding of the environment in which Oort cloud objects exist, a region characterized by extremely weak solar influence, low particle densities, and exposure to the galactic environment. The Voyagers have shown that the outer solar system is far from empty. Even at hundreds of AU, it contains a tenuous but measurable environment that interacts with objects passing through or residing in these distant reaches. These measurements help scientists model the forces that shape Oort cloud dynamics, including how comets can be perturbed by galactic tides or influenced by passing stars. The New Horizons mission, which famously flew past Pluto in 2015 and later explored the Kuiper belt object Arrokoth in 2019, adds another layer to our understanding of the solar system's edge. While New Horizons has not approached the Oort cloud, its trajectory and instrumentation provide valuable context for the outer solar system environment. New Horizons continues to travel outward at roughly 14 kilometers per second, gradually extending our direct exploration deeper into the outer reaches of the Sun's gravitational domain. The spacecraft's measurements of particle densities, dust, and radiation levels in the outer solar system enhance our models of how the environment transitions from the Kuiper belt to the far more distant Oort cloud. By characterizing this intermediate region, New Horizons helps bridge the observational gap between the known outer planets and the largely theoretical domain of the Oort cloud. Despite these remarkable achievements, the gap between our farthest traveling spacecraft and the Oort cloud remains staggering. The inner Oort cloud starts at around 2000 AU, which is nearly 20 times farther than Voyager 1's current distance, and the outer reaches may extend out to 100,000 AU. At the speeds these spacecraft travel, it would take tens of thousands of years to reach the inner Oort cloud, and potentially millions to reach its outermost regions. This reality underscores the immense scale of our solar system, highlighting that while we have reached interstellar space in terms of heliospheric boundaries, the Sun's gravitational domain stretches far beyond anything humanity has physically explored. It also emphasizes why direct observation of Oort cloud objects is so difficult. The distances involved are immense, and current propulsion technologies are orders of magnitude too slow to provide close-up exploration within human lifespans. The Voyager's and New Horizons missions do more than measure the physical environment. They also provide a baseline for understanding the solar system's protective bubble and its interaction with the galaxy. By observing the heliopause, termination shock, and outer heliosheath, these spacecraft help us infer the conditions under which Oort cloud objects exist. For example, they provide insight into the density and pressure of particles, the intensity of cosmic rays, and the structure of magnetic fields, factors that influence the stability and perturbation rates of Oort cloud objects. These data allow astronomers to refine models of how comets are nudged toward the inner solar system, how the cloud maintains its spherical distribution, and how interstellar forces shape this distant region over billions of years. The missions also underscore the technological and conceptual challenges of studying the Oort cloud. While Voyager and New Horizons provide critical in situ data for the outer solar system, the Oort cloud itself remains effectively unreachable with current spacecraft technology. The immense distances mean that even a mission traveling at the velocity of New Horizons would require millennia to arrive at the inner Oort cloud, making direct exploration a long-term aspiration rather than an immediate possibility. Nevertheless, these missions lay the groundwork for future endeavors, demonstrating the feasibility of deep space exploration, providing essential data for trajectory planning, and offering a model for the types of instrumentation that could one day study Oort cloud objects in situ. In addition, these spacecraft demonstrate the importance of combining observational data from multiple sources to study distant regions. While telescopes allow us to detect comets as they approach the inner solar system, spacecraft like Voyager and New Horizons offer direct measurements of the solar wind, magnetic fields, and interstellar particle flux that affect those comets during their journey. This synergy between remote observation and in situ exploration provides a fuller understanding of the outer solar system's dynamics and highlights the Oort cloud as an active, interacting region rather than a static shell. It also suggests that future missions, perhaps equipped with more advanced propulsion systems or autonomous observation technology, could one day traverse portions of the inner Oort cloud, directly sampling its objects and yielding unprecedented scientific insights. Ultimately, Voyager and New Horizons remind us of the vast scale and complexity of our solar system. They show that while we have made extraordinary progress in reaching the edges of the Heliosphere, the true boundary, marked by the Oort cloud, remains a distant, largely unexplored frontier. These missions illuminate the challenges of studying this icy, remote region and provide critical groundwork for modeling the Oort cloud's structure, composition, and dynamics. Each data point they collect extends humanity's knowledge outward, bringing us incrementally closer to understanding the outermost reaches of our Sun's gravitational dominion and preparing us for the eventual exploration of the solar system's quiet, icy frontier. The outermost reaches of the solar system, particularly the Oort cloud, are not just home to comets and icy planetesimals. They may also harbour theoretical objects of far greater mass, including massive rogue planets or unseen planetary companions. While no such object has yet been directly observed, several lines of indirect evidence and theoretical modelling suggest that massive bodies could exist in the Oort cloud, subtly influencing the trajectories of comets and the overall dynamical structure of this distant region. The possibility of these massive objects has intrigued astronomers for decades because they offer explanations for anomalies in the orbital distribution of distant solar system objects, unusual comet paths, and the gravitational shaping of the inner Oort cloud. One of the most discussed candidates for these theoretical objects is the so-called Planet 9, which, if it exists, could have a mass several times that of Earth and occupy a highly elliptical orbit far beyond Neptune and the Kuiper belt. Planet 9's gravitational influence might extend into the Oort cloud, perturbing icy bodies and helping to explain the clustering of certain extreme trans-Neptunian objects. While Planet 9 remains hypothetical, its potential existence illustrates the principle that massive hidden objects in the outer solar system can subtly alter the orbits of smaller bodies without being directly visible. This has led astronomers to consider the possibility of additional, less massive planets, or even rogue planetary mass objects drifting within the outermost regions of the Oort cloud. Rogue planets, in particular, offer a fascinating theoretical scenario. Unlike planets bound tightly to the Sun, rogue planets are objects that may have been ejected from their original orbits, either during the chaotic formation of the solar system or through interactions with passing stars. Some of these objects could have been captured by the Sun's gravity at great distances, becoming long-term, yet essentially hidden, members of the Oort cloud. The presence of such massive bodies could influence the orbits of surrounding comets and icy objects in subtle ways, slightly nudging them onto inward trajectories, or contributing to the occasional influx of long-period comets into the inner solar system. While direct detection is improbable with current technology, due to their faintness and distance, their gravitational signature could be inferred through careful study of cometary orbits and the statistical distribution of Oort cloud objects. Another class of theoretical objects considered in the outer solar system are primordial black holes or massive compact halo objects, MACOs. These hypothetical entities could exist in low numbers in the Oort cloud, remnants of the early universe or captured interstellar bodies, adding further complexity to the gravitational landscape. While purely speculative, such objects might occasionally interact with Oort cloud comets, causing dramatic orbital changes or even ejections from the solar system. The study of these possibilities encourages astronomers to think beyond traditional planetary dynamics and consider the outer solar system as a dynamic, interacting region where unknown forces and objects could be shaping the behavior of comets and icy bodies. Theoretical objects in the Oort cloud also include extremely distant low-mass planets, sometimes referred to as ice dwarfs or minor planetary bodies, that remain undetected due to their faintness and slow orbital motion. These objects, while individually small compared to Planet 9, could collectively exert significant gravitational influence over vast regions of the inner Oort cloud. Over millions of years, such bodies could subtly shepherd or perturb comets, maintaining some of the observed structural patterns in the distant solar system, while remaining effectively invisible to current observational instruments. Their hypothetical presence suggests that the Oort cloud is not simply a diffuse shell of comets, but may host a complex hierarchy of mass, from tiny icy objects to planetary mass bodies. Moreover, the idea of these theoretical objects highlights the dynamic interplay between the Sun and the galactic environment. Objects in the outer Oort cloud exist at the edge of the Sun's gravitational dominance, making them highly susceptible to perturbations from passing stars, molecular clouds, and the tidal forces of the Milky Way. A massive, hidden planet or rogue object within this region could amplify or modulate these external influences, acting as a gravitational intermediary. For example, a comet nudged by a passing star might first encounter a massive Oort cloud object, altering its trajectory in unexpected ways before entering the inner solar system. This possibility illustrates the rich complexity and interconnectivity of forces shaping the Oort cloud, and why it continues to be a frontier for theoretical and observational astronomy. Speculation about massive or rogue objects also raises intriguing questions about the solar system's formation history. Some of these bodies may have formed alongside the known planets, only to be scattered outward into distant, long-term orbits during early planetary migration. Others may have been captured from interstellar space during close stellar encounters in the Sun's early stellar neighborhood, effectively adding alien planetary bodies to the solar system's distant periphery. The presence of such objects could provide critical clues about the chaotic processes of planetary formation, early stellar interactions, and the solar system's evolution over billions of years. They represent a hidden dimension of the solar system that is not immediately observable, but has likely played a role in shaping the trajectories and distribution of comets we observe today. In addition, the study of theoretical massive objects in the Oort cloud has broader implications for our understanding of planetary systems beyond our own. If hidden planets or rogue bodies exist in the outer solar system, it suggests that similar unseen populations may exist around other stars, influencing cometary populations and the architecture of those systems. The study of these possibilities encourages comparative planetary science, helping astronomers to develop models that can explain both observed and unobserved structures in distant stellar systems. By considering what might exist in the unseen regions of our solar system, scientists can refine their expectations of exoplanetary environments. Understanding that vast reservoirs of icy bodies and hidden massive objects may be common features throughout the galaxy. The concept of theoretical objects in the Oort cloud underscores the profound mystery and opportunity that define the solar system's edge. It is a region that is still largely invisible, yet its existence is inferred through gravitational effects, long-period comet trajectories, and anomalies in the distribution of distant bodies. The possibility of massive planets, rogue planets, or other exotic objects hiding in this icy frontier transforms the Oort cloud from a static shell of comets into a dynamic and potentially populated region, full of gravitationally interacting entities that have remained concealed for billions of years. This hidden dimension emphasizes that the solar system's edge is not merely a boundary, but a complex environment with enormous potential for discovery, waiting for future generations of astronomers and spacecraft to illuminate its mysteries. Exploring the Oort cloud represents one of the most formidable challenges in human space exploration, yet it is also one of the most compelling frontiers, offering the potential to directly study primordial materials, comets, and perhaps even hidden massive objects at the edge of our solar system. Given that the inner boundary of the Oort cloud begins at roughly 2,000 astronomical units, AU, and its outer reaches may extend up to 100,000 AU, any mission to this distant region would require revolutionary propulsion technology, long-duration spacecraft systems, and autonomous operational capabilities that far exceed anything currently available. However, scientists and engineers have begun to conceptualize how humanity might one day send probes to this remote, icy frontier, combining advances in propulsion, energy generation, miniaturization, and artificial intelligence to overcome the immense distances and logistical challenges involved. One of the most widely discussed concepts for reaching the Oort cloud involves the use of solar sails or light sails, which would utilize the pressure of photons from the sun or even directed laser beams to propel small, lightweight probes to significant fractions of the speed of light. By harnessing continuous photon pressure, a solar sail could gradually accelerate over decades, eventually reaching velocities high enough to traverse thousands of AU within a human lifetime. While such a mission would likely begin with a small, ultralight probe, it could carry high-resolution imaging systems, spectrometers, and particle detectors to study the composition, structure, and dynamics of Oort cloud objects as it passes through the region. These solar sail-driven probes would represent the first steps toward true interstellar precursor missions, capable of reaching distances beyond the heliopause and venturing into the Oort cloud while remaining technically feasible with near-future technology. Another approach involves nuclear propulsion, particularly systems based on nuclear thermal or nuclear electric propulsion. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant such as hydrogen, producing high exhaust velocities and significantly reducing travel time compared to conventional chemical rockets. Nuclear electric propulsion, on the other hand, uses a nuclear reactor to generate electricity, which then powers highly efficient ion engines capable of continuous low-thrust acceleration over extended periods. Such systems could enable larger probes equipped with more comprehensive scientific payloads to reach the inner Oort cloud within several decades, rather than centuries or millennia. These propulsion methods would allow the spacecraft to carry instruments capable of detailed chemical and isotopic analysis of icy bodies, direct imaging of distant objects, and measurements of the local interstellar environment, transforming our understanding of the solar system's outermost regions. Advances in autonomous navigation, artificial intelligence, and miniaturized instrumentation will be essential for any Oort cloud mission. Given the extreme distances, communication delays between Earth and a probe could range from several days to weeks, requiring the spacecraft to operate independently for extended periods. AI systems would need to manage navigation through the sparse but complex environment of the Oort cloud, identify and prioritize objects for observation, and handle unexpected anomalies without direct human intervention. Miniaturization of scientific instruments is also critical. Smaller, lighter payloads reduce the mass that must be accelerated to high velocities, making solar sail or nuclear-propelled missions more feasible. Advances in materials science, particularly the development of radiation-hardened components and long-life power sources, are likewise necessary to ensure the survival and operational capability of probes over the decades-long journey to the Oort cloud. A further concept involves swarm-based missions, in which multiple small probes are launched together, each tasked with studying different aspects of the Oort cloud environment. This approach spreads the risk of mission failure, increases coverage of the vast and sparsely populated cloud, and allows for a more comprehensive survey of distant icy objects. These swarms could communicate among themselves, creating a distributed network of observation that transmits aggregated data back to Earth at manageable intervals. Swarm missions would also allow for in situ sampling of multiple comets or small bodies, enhancing the scientific return and potentially uncovering evidence of hidden massive objects or rogue planets suggested by indirect gravitational effects. The use of gravity assists from planets in the inner solar system could also play a role in future Oort cloud exploration. By carefully planning trajectories that utilize the gravitational pull of Jupiter, Saturn, or other massive planets, a spacecraft could gain additional velocity without expending extra fuel, effectively slingshotting it toward the outer solar system. Such maneuvers, combined with advanced propulsion technologies, could reduce the travel time to the inner Oort cloud from centuries to decades, making the mission more practical within the context of human lifespans or multi-generational project timelines. In addition to propulsion and navigation, energy generation for long-duration Oort cloud missions is a critical consideration. Solar panels become ineffective at the immense distances of the Oort cloud due to the sun's reduced intensity, necessitating alternative energy sources such as long-lived radioisotope thermoelectric generators, RTGs, or nuclear reactors. These power systems would need to sustain onboard instruments, communication equipment, propulsion units, and thermal regulation systems over potentially decades of travel. RTGs have already demonstrated long-term reliability in missions like Voyager, Cassini, and New Horizons. But missions to the Oort cloud would require enhancements to power efficiency and longevity to maintain functionality at distances hundreds of times farther than Pluto. Direct sampling or flybys of Oort cloud objects present additional challenges and scientific opportunities. Given the extremely low temperatures and faint solar illumination in this region, instruments must be capable of detecting and analyzing objects with minimal reflected light and weak thermal emission. Advanced imaging systems using high-sensitivity detectors, coupled with spectroscopic instruments capable of discerning the composition of ices, dust, and organic compounds, could reveal critical details about the chemical and isotopic composition of Oort cloud bodies. Such data would provide unprecedented insights into the primordial materials of the solar system, revealing the preserved building blocks from the era of planetary formation, and offering a window into processes that shaped the solar system billions of years ago. Future exploration may also consider in situ experiments, such as small penetrators or sample return capsules designed to collect material from comets or icy bodies. While a full-scale sample return from the Oort cloud remains technologically daunting, even partial in situ analysis could answer fundamental questions about the presence of complex organics, volatile distribution, and isotopic signatures, providing clues to the origins of water and life on Earth. By combining direct observation, sampling, and long-duration monitoring, a probe mission to the Oort cloud would represent one of the most ambitious and transformative undertakings in the history of space exploration. The possibilities for future exploration of the Oort cloud are vast but demanding. Concepts range from ultralight solar sail-driven probes and nuclear-propelled spacecraft to AI-guided swarms and gravity-assisted trajectories, each requiring innovations in propulsion, energy generation, autonomy, and instrumentation. Despite the enormous distances and long timescales involved, these missions hold the promise of revealing the secrets of the solar system's most remote frontier, a frozen, dynamic, and largely unexplored region that contains ancient relics of planetary formation, potential hidden planets, and the origins of long-period comets. The vision of exploring the Oort cloud transforms it from a theoretical construct into a tangible objective for human curiosity and ingenuity, one that could fundamentally reshape our understanding of the solar system's formation, evolution, and interaction with the galaxy. The Oort cloud stands as one of the most profound reminders of the vastness and mystery of our solar system. It is a realm that few have glimpsed even indirectly, a remote shell of icy bodies orbiting the Sun at distances so immense that they challenge our ability to comprehend space itself. These frozen objects, relics from the dawn of the solar system, preserve a record of conditions and materials that existed billions of years ago, long before the planets fully formed and long before life emerged on Earth. Each long-period comet that ventures inward from this distant cloud carries a fragment of that primordial history, a messenger bridging the gap between the darkness at the solar system's edge and the warmth and light of the inner planets. The sheer scale of the Oort cloud amplifies its sense of awe. Extending potentially as far as 100,000 astronomical units from the Sun, it marks the outermost gravitational boundary of our stellar neighborhood. Beyond this point lies the true interstellar void, a space dominated by the gravitational and magnetic forces of the galaxy rather than the Sun. Within this frozen expanse, the ordinary rules of the solar system, planetary orbits, solar radiation, and magnetic influence fade into insignificance. The objects within the Oort cloud drift slowly, governed by weak solar gravity, occasionally perturbed by passing stars, galactic tides, or the gravitational pull of hypothetical massive objects. In this sense, the Oort cloud is both the end of our familiar solar system and the beginning of the unknown, a liminal space at the interface between the local and the cosmic. The quietness of the Oort cloud is perhaps its most haunting feature. Unlike the inner solar system, where planets clash, comets streak, and asteroids collide, the Oort cloud is largely serene, a frozen wilderness where processes unfold over millennia rather than days. It is a place where time seems to slow, where icy bodies drift undisturbed in near total darkness, and where the Sun's influence is reduced to a faint gravitational pull. Yet, within this apparent stillness lies tremendous potential for revelation. Every comet that leaves the Oort cloud, every trajectory subtly altered by unseen forces, hints at the complex interplay of gravity, galactic tides, and perhaps even hidden planetary mass objects. The Oort cloud, in its silent majesty, is a dynamic system that connects the inner solar system to the broader galactic environment. Our understanding of this distant frontier is limited but growing. Missions like Voyager and New Horizons have provided glimpses into the solar system's outer reaches, revealing the edge of the Heliosphere and the interactions between solar and interstellar space. Observations of long-period comets provide indirect evidence of the cloud's structure and population. Theoretical models suggest a rich and varied environment, potentially containing hidden massive objects or even captured rogue planets. Future exploration concepts, from solar sails to nuclear-propelled probes, promise to extend humanity's reach into this remote domain, offering the possibility of direct study and unprecedented discoveries. Yet despite all these advances, the Oort cloud remains largely out of reach, a reminder of the limits of our technology and imagination. There is a profound philosophical resonance in contemplating the Oort cloud. It is a boundary not just of space, but of knowledge, a physical manifestation of the outer limits of human observation and understanding. In studying it, we confront the enormity of the cosmos and the fragility of our presence within it. The Oort cloud challenges us to expand our perspective, to imagine worlds beyond our immediate sensory experience, and to recognize the enduring mysteries that lie at the edge of what we know. Its icy bodies, drifting in the darkness, are silent witnesses to the birth of the solar system, the migrations of planets, and the subtle forces that continue to shape our cosmic neighborhood. Ultimately, the Oort cloud embodies the essence of exploration and curiosity. It is the quiet frontier, a frozen expanse at the very limits of the Sun's reach, filled with ancient comets, icy relics, and possibly unseen massive objects. It invites us to dream of the missions that could one day traverse its depths, to consider the secrets it holds about the origins of the solar system, and to marvel at the vast scales of space and time it represents. The Oort cloud is a place where the familiar gives way to the mysterious, where the edge of our knowledge meets the infinite possibilities of the cosmos. In the end, as we peer into this remote wilderness, we are reminded that the solar system is far more than the planets we see. It is an expansive, dynamic, and largely unexplored frontier. The Oort cloud is the ultimate symbol of that frontier, quiet, distant, and enigmatic, hinting at the countless mysteries still waiting to be discovered, waiting to reveal the hidden stories of our cosmic past. Its frozen bodies orbit silently in the dark, carrying within them the history of our Sun and the building blocks of the solar system, and perhaps even clues to the origins of life itself. The Oort cloud is the quiet frontier, a vast icy wilderness at the edge of our solar system, hinting at the mysteries still waiting to be discovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.